Hello. In this video, we're going to discuss the dynamic behavior of ideal systems. So essentially what we're going to do is we're going to use transfer function models and we're going to predict the dynamic response of processes to step input changes. Okay, so we're going to do this for a couple different types of processes. So for the first process, we'll look at an integrating process, and we'll discuss what that is. The second type, we'll discuss first order processes. And again, this could be a first order, or we can also evaluate first order plus dead time. And then the third example that we'll do is a second order process. And again, this may have dead time associated with it as well. Okay, so the purpose here is we're going to use transfer function models. So a transfer function is a relationship in the Laplace domain So it's a relationship in the Laplace domain that relates an output variable, we're going to call that y, to an input variable u. Okay, and for what we're going to look at here is we want to know the dynamic behavior. So what the dynamic behavior means is the time-dependent response. So the time-dependent response would come from this system right here, where if we took the transfer function in the Laplace domain, multiplied it by the input function, and remember, we said we're going to do step changes in the input, which would be something like a over s, where a is the step change. But then, so knowing the transfer function, we can take the inverse Laplace of these and get back to y of t. And essentially, this would tell us essentially the dynamic behavior, or the time to how the function varies with time. So what we're going to do here is we're strictly going to say we're going to go through an analysis where if we know the transfer function, which is just the function in the Laplace domain, we can predict the dynamic behavior to a step input change. And so based on the transfer function, we can predict y of t for these various processes, integrating first order plus dead time, or second order plus dead time. Now we can also go in the reverse direction. So if we know the dynamic behavior, so for example, if we have process data, an example of process data might look something like this. You know, we're working on a process, and on the right axis we're going to look at the input variable, and maybe the input variable might be like a entering flow rate. So if we apply at time equals 0, so this right here would be time equals 0. If we apply a step input change, and then this would just be some sort of arbitrary change a, we can measure, and we measure the process variable. So for example, the temperature. Actually, this right here should be f of t in the time domain. We'll measure we can collect data for the temperature if the temperature is the output variable, and the temperature might look something like this. Okay, so essentially based on the behavior of this system, we can predict what the transfer function is through the methods that we're going to do. And we can do this for these various types of models. The first process I want to look at is called an integrating process. So again, we have an integrating process, and we're going to go ahead and we're going to derive the actual, so integrating process. So we're going to actually derive the model itself. So an integrating process might be a process like this, where we have maybe two streams that are being mixed together, and then for this stream we have a valve on the outlet. We'll call this F. Okay, and so for this process, what we want to do is we want to achieve level control. So level is going to be our primary control variable, and we want to achieve level control with the outlet volumetric flow rate, and we'll call that FV. Okay, so the model for this process is we can derive it based on the mass balance. So we have dm dt, so this is the mass inside the tank, equals the mass flow rate in, so that's going to be F1 plus F2 minus the mass flow rate out, which is F. Okay, so we know that the mass equals the density times the volume. We want to convert this to level, so the volume is going to be the cross-sectional area, assuming it's a cylindrical tank, which most are, times level. Okay, and so then for F, for the flow rates, these are written in terms of mass flow rate, so to convert them to volumetric flow rate, we're going to do density times volumetric flow rate, and we can check this because density is mass per volume, and volumetric flow rate is volume per time, right? And this would give us our mass flow rate of mass per time. All right, so I'm going to put these over here into the equation. So now the density, also we're going to make an assumption here that the density is constant. So we're going to assume constant density. So let's see, so inside the derivative term here, this is going to become rho AC, because that's constant, dl dt, equals rho FV1 plus rho FV2. Let me erase this. Minus rho F V, okay, because again, this is going to be our input variable. These right here are going to be treated as constants. Now again, for this process here, because we're controlling the level, we're not assuming that it's constant volume process. So FV does not have to equal FV1 plus FV2. All right, so now the next few steps, or we can go ahead and cancel out rho in each one of these because rho is constant. So to derive the transfer function for this process, we first convert to deviation variable. The next step we do is we subtract out the steady state or initial condition. And then the third thing we do is we take the Laplace. And if we do those three steps, we end up with AC, cross-sectional area, times S times LS, and this again deviation variable equals, these are constants, so they come out from when we apply the steady state condition, equals FV in the Laplace domain. And again, the transfer function for this process is output, which is level, over input, actually this is going to be negative FV, which is FV S. So again, this is what we're looking for. So again, if we go ahead and we divide through, bring FV over this side, AC S over to the other side, we get our transfer function for this process is going to be -1 over cross-sectional area, which is AC, times S. Okay? So that's what we have. All right, so now the next thing we want to do is our goal is to sketch the dynamic response of the level for a step increase in the flow. Okay, and we'll do that on the next page. Okay, so remember that our transfer function G equals -1 over ACS. Okay, so to plot this system, so again, it's an integrating process, so we have time on the bottom axis. I'm going to set time equals 0 here. So we're going to have a step change, and we'll just give a number to that. We'll call that 2. Over on the right axis, we'll call this our FV, so it's our flow rate. And this is just 2 in terms of arbitrary units. I mean, we could say 2 gallons per minute. All right, so how do we get how do we sketch the level? How does the level respond for an integrating process? Now, we don't necessarily have a method for doing this, but we have knowledge about how this is going to work. If I do a step increase in the outlet flow, I would expect the level of the tank to decrease. So I'm going to start up here, and I'm going to call this L0. So this is the level before the time was changed. And if I have a step change in 2 gallons per minute, that means I would expect to have a linear decrease in the outlet flow. So this is going to be linear. So now I'm going to leave it up to you. Okay, in general, this is going to be linear until the tank empties out, because if the outlet flow is 2 gallons higher than the inlet flow, eventually the tank is going to exit, and anything that comes in the tank is automatically going to exit, so it'll stay empty. So this slope should be linear, and I'm going to ask you, what is the slope? Use your understanding of the model to figure out what the slope is for this process. Another question I could ask is, what is U of S, or F of S? So what is the input in the Laplace domain, right? So the input for a step change in the Laplace domain, this would be 2 over S. All right, so let's look at some sensor type models or other types of models. So this next model that we'll discuss is a dead time model. So we'll look at a dead time model. So assume here that we have a sensor. So the problem statement is we have a sensor with a dead time of 5 minutes. So here we can do the same thing. We're going to sketch the dynamic behavior of the sensor with respect to a step input change of, we'll say 3 degrees per minute. So step input of 3 degrees C. So how do we do this? We don't really have a model for this, but we have intuition of what it would look like. Actually, this is a dead time model. So instead of doing a temperature model, or instead of doing a temperature example, let's do a concentration, because a concentration sensor is more likely to have a sampling system or a dead time model. So we'll do a step input change of 3 mole per liter, or 3 molar. So again, if we want to think about a sensor, if we have a sensor, going into the sensor is the composition, coming out of the sensor is the sense composition. So this would be like a step input change of the process of 3 gallons per minute, and we want to see how the sensor actually responds. So again, we can go ahead and plot this. Okay, and I'm going to plot them both on the same side. So this is time. So at t equals 0, there's a step input change of composition. This is the composition, and this step input change is 3 molar. Okay, so then how would our sensor respond? So essentially it's just going to be a dead time. So our model, our time-dependent model, is C of t, Cs of t, equals the composition at 5 minutes ago. So again, so there's going to be a dead time. So 1, 2, 3, 4, 5. After 5 minutes, this is going to give us the same value. So our plot of the dead time model is essentially going to look just like that. And then it's going to read the same value. All right, let's now stay on sensors, but now let's do a first order model. So here, so we have a sensor. So the problem statement is that we have a sensor with a time constant of 1.5 minutes. Okay, so we want to sketch, again, we're going to do the same thing. We're going to, based on the model or the transfer function, we are going to sketch the dynamic behavior. So again, for this system, we know if we have a first order sensor, the transfer function for a first order sensor is going to, or any first order process, is going to be the gain. And so we'll just say gain of the sensor, Ks, over tau S, tau, time constant of the sensor, times S plus 1. Okay, we also know for a sensor, the gain of a sensor should be 1, because if the input changes by 5, we expect the sensor value to change by 1. And we have tau S equals 1.5. So instead of writing tau S here, I'm just going to write this as 1.5. Okay, so this is our transfer function. And so based on this transfer function model, we can now sketch the dynamic response of the temperature of the, for example, temperature. So again, we'll do the same thing. Here we'll plot time, we'll have t equals 0 right here, and we have a step input change of our control variable, and we'll just call this 3 arbitrary units. And if it's a sensor, it would be maybe degree C. Okay, so then again on this side over here we have our input. Our input is u, and again it's u as a function of time, so this is going to be our input. And then over on this side we're going to have our control variable, or our output variable, which is y, for example temperature. So we know that then if at t equals 0, the process is going to start to change, and it's a first order. And we can essentially go through the method we discussed last time to sketch the dynamic behavior of the system. And so the couple of points of interest is that at time equals infinity, we can use the gain to calculate what's the overall change in the process. So for a sensor, because the gain is 1, we know eventually at some time equals infinity, our overall process should have an overall change of 3. Right? If our gain were 2, then the process would change by 6. So this value right here is essentially going to be the gain. So in this case, the gain of the sensor times delta U, how much the overall process changes. Okay, then we also know that at 1 tau, the process is going to change by 63% of the total change. At 3 taus, it's going to be 95%. So I'm going to say this is 2 taus. So 2 taus is going to be 3. We'll just kind of write these on here like this. Okay, so at 1 tau, we would calculate 63% of 3 and put a point right here. At 3 tau, we would calculate 95% of 3. So again, this point right here is 0.63 times 3. This point right here is 0.95 times 3. Now once we have those points right there, we can sketch this plot. And this would give us a pretty good fit of what we would expect the dynamics of the system should be. And now note, for a purely first order process, it should be the steepest at the beginning, and then eventually exponentially decay towards the new set point. All right, so that's a first order model. So for my last example, we're going to look at a process response, and we're going to use the previous method we talked about to derive a transfer function for that experimental, we'll call it process data. Okay, so here we're given data, and so the data that we're given, and I'm going to try to sketch it out on here and write it neat enough that we can read it. We'll have, again, t equals 0, and again we have a step change in our input, so that should be constant over here. The step change is 2 gallons per minute. So our input over here on the right axis is going to be a flow rate, or volumetric flow rate. So this is the volumetric flow rate as a function of time. Step input change at t equals 0. So then we're going to have our process data over on the left-hand axis. And so we're going to do this, we're going to call this temperature, and we'll say it's in deviation variable form. So we'll have this start at 0, and then I'm just going to do increments of 5, 10, let's go 5, 10, 15. Okay, so we start at 0, and the process is going to respond, our process, and then, okay, we're going to also have down here increments of, these increments that we write down here will be 2-minute time increments, so this interval on the bottom will be 2 minutes. So I'm going to kind of draw our process response. I'm kind of sketching it, just sort of making something up a little bit as we go. 2, 4. So I'm trying to make this set up before. 1, 2, 3, 4. Another one over here. And then also we'll have things in between here. So the process will respond and look like this. We have a slow turn on, overshoot up to about 15, come back down, and then oscillate a little bit and eventually kind of settle out. Okay, so that's, looks okay for what we're trying to do here. So again, this is in terms of the deviation variable is a function of time. So at 0 in terms of the deviation variable, this is 5, 10, 15. Make this look more like a 10. This right here would be like our T naught. All right, so our goal is, given this process data, so we collected data for the process, is we want to get the transfer function for this process. Okay, so the first thing is we know is that because we have oscillations, we have to treat this as a second order process. Because our only options are integrating, which this is not, first order plus dead time, so this is not first order. So this is either going to be second order or second order plus dead time because of the oscillations. So I'm going to go ahead and just write the transfer function over here in the generic form. So it's gain over tau p squared s squared plus 2 tau p zeta s plus 1. Okay, so these are going to be terms that we can figure out from this data. And because I don't know if it has dead time or not, I'm going to also just assume for now that it has dead time. If it doesn't have dead time, this term right here, dead time will be 0, exponent of 0 is just 1, so that will cancel off. But I'm going to put it here because this may or may not have dead time. Okay, so the first thing that we're going to do is we're going to determine the characteristics. We're going to determine the characteristics from the plot. So that's our first step. Is we need to know what are and these are essentially the data, the characteristics of the data, not the characteristics of an ideal model or the characteristics of the transfer function. So first, or I guess one thing that we could do, we're going to do the characteristics of the data. So the first thing is we have what I called R, and R is going to be the time that it takes to cross the new steady state value. So if we draw a line down here, it's going to be somewhere right here. So this right here is going to be R. So one of our characteristics is R equals, because these are 2-minute increments, 3 of them is going to be 6 minutes. We can also write, so D, which is going to be the overall change in the parameter, so it goes from 0 to 10, so this is going to be 10. Maybe if this is in temperature, it would be degrees C. We also are going to get our overshoot, which is B. So our overshoot, it goes up to 15, so it's going to be 15 minus 10 is 5 degrees C. Other characteristics are going to be T, the period of oscillation. So the period of oscillation, it would go right here, from here to here, so this is T. And so T for this process is going to be 4 intervals of 2, so this is going to be 8 minutes. And I think that's all that we have that we need. And we can also note that our delta U is equal to 2. And so D, which is equal to 10, this is also equal to our delta Y, the total change in Y. Okay, so now what we can do is we can get, the next step is to get our parameters, to get our model parameters. Typically the easiest one to get first is the gain, so the gain is going to be delta Y, which is also going to be D divided by delta U. And so the gain for this is going to be 10 over 2, which is 5. The next thing we can do is get the zeta is the next easiest thing to do. So to get zeta, we can use the overshoot, so B over D. This will tell us our data, and so the equation to get that is B over D equals the exponent of negative pi times zeta over root 1 minus zeta squared. So from here we can go ahead and calculate, or this also, B over D equals 0.5. So from here we can calculate zeta. I'm not going to do that right now, but that's how we'll get it. Next we can use the period of oscillation. So the relationship for period of oscillation is going to be T equals 2 pi times tau p over square root of 1 minus zeta squared. So now knowing zeta, we can plug that in there, and so from here we can go ahead and calculate tau p. All right, the next thing we also need to do, so we have, this would give us gain, zeta, and tau p. So this gain, we can again plug it up into the model, zeta plug up into the model, tau p plug up into the model. The last thing that we don't know is whether or not we have this dead time term, zeta, or theta. But what we do know is that the plot characteristic R would be equal to theta plus t rise. So t rise is the time that it takes a theoretical second order model to cross the new steady state value. We don't know if this is a theoretical model or not. So this could just be equal, R could be equal to t rise, or R could be something smaller than t rise. If R is less than t rise, we know what the dead time for this is. So we can calculate t rise now. So t rise is going to be, the equation is tau p times pi minus phi over square root 1 minus zeta squared. And then we can also get phi equals inverse tangent of square root 1 minus zeta squared over zeta. So again, knowing zeta, we can calculate phi, plug phi in here, get t rise. Let's assume for now that t rise equals 3. So we're going to say we calculate it, and I didn't actually do this, so t rise equals 3. If t rise equals 3, then I know that theta equals r, which is going to be 6 minutes, minus t rise, which is 3 minutes, which would be 3. So that's how it gets theta. If it turns out that t rise is 6, then I know that there's no dead time, and I can essentially scratch this term off, and then I have the terms for my overall transfer function. All right, so that's how we use process data to get a transfer function. Now, again, we just did this for a couple cases. I could be given the transfer function shown here, and I would just go in the opposite direction. I would use these values to calculate, the characteristics of the plot, and then I would put the characteristics of the plot on here, labeling as best I can based on t rise and dead time. So we can do this for first order plus dead time, first order. So the thing that I'll kind of leave with is that if this were a model that looked like, if it were something that looked like this, we would assume this is a first order plus dead time model because a first order model is always going to start off the sharpest at the beginning. If there's any sort of delay for a first order model, the assumption has to be is that it has dead time in it. Okay, so we'll stop there and we'll see you next time.